Okay, so hopefully you should see this message of recording start. Okay, hi everyone, welcome to part B of the MSRI Summer School on Foundations on Frontiers of Probabilistic Proofs. I'm Tom Ger, and I'm going to tell you in this lecture about probabilistically checkable proofs, which we just call PCPs. And this is going to be a very relaxed and laid-back lectures, not too many technical details, and the lecture starting tomorrow will get more mathematical and it will be more a little bit more intense. Okay, so let's start with something more general, which is the evolution of mathematical proofs, which is something I kind of like. I was interested. I read a bit about the history of how we came about this notion of mathematical proofs. It's rather an interesting thing. And apparently, I was surprised too, the notion of a proof as we have it today is extremely different than what it was, I don't know, 200 years ago, let alone 2000 years ago. So it's been quite a bit of a process. So let me start, over 2,500 years ago with Thales of Miletus. And just curious, did anyone ever heard about Thales?
Yes.
Okay, so hopefully you don't know more about Thales than me, but the idea is that he is the first recorded mathematicians in history, or rather the first person that we know that there are documents showing his mathematical work. And he was, like most mathematicians in that area, he was primarily a philosopher. Now, funny thing is that if you recall, in the other lecture, Ale started by saying, we have proofs as we know them today, and they got at some point, in like about 40 years ago, we had this re-envisioning of proof systems, and we said, maybe we can do things with interaction, maybe we can do things with randomness. So apparently, even in the time of Thales of Miletus, the notion of proof was very different. Philosophers used to present their arguments as a conversation. You can see it a lot in the writing of Socrates. So in many sense, the type of proofs that he had for mathematical statements, though we don't have concrete evidence for, not a lot of the writings remain, but they were of that sort, so kind of even more similar to interactive proofs than the proofs that we see today. And at that time, the whole notion of a proof just began to formulate. So what does it mean to a proof? How do we, is it enough to show examples? Do we need to have this like chain of derivations to do it? Can it be an argument which holds with certain probability? That was still forging. Okay, so next, Euclid came, and in one of the most influential texts in all of mathematics, the Elements, he produced the geometry that most of us learned in high school. And what was remarkable about that work, more than the geometry that it outlined, was that the work puts down the foundations of starting with some axioms and using these axioms to make deductive rules. So a linear type of, rather than a conversation or anything of this sort, or examples, it was we start with certain axioms and then we derive and derive and derive until we reach a proof. Okay, the next person we'll see is Al-Khwarizmi, who his anglicized name became algorithm in writing. And in the text that Al-Khwarizmi had, the approach for proof was rather different than strictly the way that you see it in Euclid's writing. And he presented things which are closer to the algorithms that we see today. So for example, if you want to prove a certain theorem, like how to compute a certain thing, then he gave a recipe that you can follow and always obtain, hopefully, the right answer. And simultaneously, or not simultaneously, sorry, like 600 years later, in India, we have Madhava of San Magrama, who used a different approach to proofs. Well, the approach was, instead of focusing on mathematical rigor, it was about obtaining formulas and getting solutions. And the idea is that he managed to make quite amazing progress that wasn't really recovered at the West for a very, very long time. But the rigor was not the one that it was accepted at the time, like in Europe. Okay, and then we're getting to more and more modern times. So this is Carl Weierstrass. And I think he's considered as the father of modern analysis in many ways, but I think one of the most important things that he gave to the evolution of a proof was that he came up with this rather, annoying counterexamples that we see. Like, for example, when we look at integrals and when we look at convergence of series and things along these lines, we always have these examples that talk about like rather catatonic and cases that you wouldn't naturally think, but this forced, it actually started what would later become an entire crisis in the foundations of mathematics, because the idea was that we need to have solid foundations and that everything can be proved and in a way that has no holes in it. So he explored lots of degenerate cases and lots of cases which defied intuition, just to show why we really need proofs which are completely sound. And finally, we have David Hilbert, who in some sense started, it's like in 1900, the Congress of Mathematics, and then he also posed his famous questions, which includes like the Riemann hypothesis and all of the rest. And he set to finally get a program where we can have a concretely solid base for mathematics and proofs, which later Zermelo, formalized, and we got like the Zermelo-Frankel axiom. So we have this like modern set of axioms, and now the notion of proofs that we have, it really is a bunch of axioms and strict derivations. Okay, so this is by no means attempting to be anything comprehensive. It's just snapshots of how proofs evolved through the years, and in some sense we now have a cycle, because we tend to look at these days, we again reimagine the notion of proof, and we try to, and we almost go back to the time of Thales of Miletus in how we perceive proofs in the computational setting. Okay, so what does it mean, a probabilistically checkable proof? So the idea is like to be able to check a proof without reading it. And it must be something important because it made it into, the New York Times, and you can see here. I hope you can see my cursor. So you can see here an article which said that we have a new shortcut to verify long mathematical proofs. So let's see what this is all about. So proofs have many interpretations, even to this day. So, concluding the line that we just discussed, you can say that if you ask Zermelo, he would tell that proofs are logical derivations from axioms. And that is what we mean in that sense, in the formal sense of a proof. However, just as valid interpretation, which I got from Irit Dinur, so she said that a proof is an approximation of understanding. So what do we mean? What does that even mean? So the idea is that when I read a proof, more often than not, I don't read it in order to convince myself that some textbook result is correct. I kind of assume that this is very well likely to be the case if hundreds of people read the proof and got convinced. The reason why I read proofs is because I want to understand. So we all have the way that we understand mathematical ideas, but it's kind of hard to put these things into words and just communicate understanding. So what we do, we just give some approximation of our understanding, and that is a proof. Now, of course, you will also see in this course the notion of zero knowledge proofs, which teach you absolutely nothing. So that wouldn't be a good match for that. But I think for the notion of mathematical proofs, this is definitely the thing. And the last interpretation that I want to mention, which is actually the one that we'll follow, is one by Shimon Even, who said, a proof is whatever that convinces me. And I think in many ways, this is a clever thing to say, because we never really go down in proofs and go down to, first order logic and like verify every possible step. So there is some human resolution that we need to make. And this perspective on convincing will be very handy in PCPs and interactive proofs as well. So I see here a question. Let me see. So just to read it out loud, it says, if interactive proofs are much more powerful than static mathematical proofs, why do we still use static proofs in mathematical analysis? How would an interactive version of Peano's proof system look like? Will such an interactive proof version of Peano's proof system will still be limited by Gödel incompleteness theorems? So off the top of my head, I think this is a fantastic question to be asked, but one which is extremely sensitive to formulation, in the sense that we need to be extremely careful regarding what do we mean to achieve by that, and the notions of interactive proofs, which are more powerful, they are powerful in a computational setting, but I think it is an interesting question to think about. Okay, so the key idea, in order to check a proof without reading it at all, would be to check proof probabilistically and allowing some negligible error. So in some sense, this should not be foreign to you at all. And what do I mean by that? Like, for example, we do it all the time when we, for example, poll voting. So suppose that you have, I don't know, some, let me see, okay. So we want to vote for some political parties. To make it less engaging, let's call these parties 0 and 1. So hopefully this would not offend anyone. And what do? We have votes. So we can think about it as, some vector. I vote for party number 1, I vote for party number 0, and so on and so forth. And, when we want to be absolutely convinced that these are like which party got the majority, we just like go over this set of all votes, which we can think about as an NP proof. And in linear time, we just like go over it and we count the number of ones and the number of zeros, and this is how we make a decision. But of course, we can also do some random polling and just check just a tiny fraction of the votes. And indeed, if we know that one party won by overwhelming majority, let's say by 2/3 of the votes, then it's enough to even sample a tiny amount of votes and be convinced with high probability. The point why checking a proof is much more challenging than that, because what happens if like the outcome of the elections is completely sensitive and tight, and we have 1 million people voting for one party and 1,000,001 voting for the other party. In such a case, being like just sampling at random will do no good at all. And the magic of PCPs, of probabilistically checkable proofs, is that it allows us to do this proof verification by sampling, even though there is no notion at all of distance in the problem that we consider. Okay. And that's exactly the caveat that I mentioned, and which brings me to what makes this thing, like the mathematical meat, the mathematical tool that allow this local to global, that allows this magic of local verification to happen. And that is local to global phenomena. So what's local to global phenomena? Here is the idea in a sentence. We want to take a proof. We want to take, maybe an NP proof, and we want to endow it with some rich, nice structure, lots of symmetry, lots of like nice properties that would be convenient for us. And hopefully, if we do that, then we'll be in a situation where we can actually check things locally and infer global information about it. Okay, so let me explain more. So here are some examples. Anyone recognizes the plot of this function? Feel free to put it in the chat. So yeah, okay, I see. So here we can look at an analytic function, a function over the complex number, which is holomorphic. And holomorphic functions have this like nice property that if you know the values of the function on a certain curve, on a certain loop, then it's enough to infer all of the structure of the function pretty much everywhere. So we have this phenomenon that we look very locally, yet we can infer something which is completely global. And other examples we can see in algebraic varieties, which, these are geometrical objects which has a lot of symmetry. So if we sample and see part of the variety, then we actually can infer a lot of information about the whole. And we also see that in fractals, where, it's like, suppose this was an animation that you can zoom everywhere, and any point contains the entire information of the entire shape. So this notion of local to global phenomena is completely not new in mathematics. But we'll apply it in what, again, Niriti likes to call the jump principle. So what's the idea here? So suppose that somebody is giving us some NP proof of our choice. And what's happening now is, well, we have let me see if I can, highlight it. Okay, just 1 second. Okay. So, and the NP proof is a toast. So you know how you can hold a toast and then you have some piece of jam on it and you want to know whether there is jam on your toast or not, but maybe, you have your eyes covered. So you can take a random bite, but then you have a low probability event of actually hitting the jam. But if you kind of smear it with a knife and spread the jam uniformly, then wherever you take a bite, you'll still be able to taste the jam on it. And this same principle is exactly what we want to do with an NP proof. So maybe we'll have an NP proof, and there would be only, one point in the proof which is bad. Like, for example, think about maybe, a graph which we claim is very colorable. And maybe an NP proof would be a coloring of this graph, and only one color would be wrong. So what a PCP would allow us to do is to take this graph, transform it into another graph, such that either everything would be completely fine and all the coloring would be perfect, or alternatively, a very large fraction of it would be would not be valid, and so it would be enough to sample. So the whole name of the game in PCPs is how can we take a small amount of error and encode it in a way that will allow us to reduce it in by just probing it locally. Okay, and I just want to give one informal example. We'll do it in 2 days, much more in depth. So I'm not, so if we don't need to follow everything, but the idea is to consider low degree polynomials. So suppose that you take some polynomial p in 2 variables, which has a degree d. Now, maybe you just write it down, the values of this polynomial at the matrix. So you take a matrix and you say, that's my polynomial p at point 0, 0, 0, 1, 0, 2, and just write down the truth table of the polynomial, evaluate it over the field. Okay, so this polynomial has this nice effect that if this polynomial is of degree at most d, and then we're only looking at a line. So what is a polynomial restricted to a line? It's a polynomial where we just, concatenate it or just compose it with a line equation. And by doing so, we don't increase the degree at all. And so we get a univariate polynomial, which is also of low degree. So what does that tell us? It tells us that, for example, if I have maybe some corruption, so let's say that I have a polynomial and somebody is claiming that this is the all zero polynomial, and I, in some point, got corrupted. So by taking a line, a random line that goes to this point, with high probability, I would, as long as there isn't too much corruption, with high probability, I will be able to, most of the points on the line will not hit the corruption, and then by just plain interpolation, one can recover the point. And as we'll see more generally, we'll also be able to say, whether a polynomial is of low degree or not, just by looking at smaller affine subspaces, like a line, and checking whether they are themselves low degree. But this is extremely, informal and high level. Just like to give you an intuition, but we'll get and do it slowly and nicely shortly. Okay, and I get another question regarding PCPs and fast Fourier transforms, and whether there is a connection. And indeed there is, and you'll get to see it in lecture number 4. So definitely check out the nice video that we posted on Slack. Okay, so let's continue and talk a bit about PCPs and start with the actual content. So, we discussed, you discussed with Ali the notion of an NP proof, where you have a prover, the prover is sending some proof, and the verifier tries to verify it, indeed. Okay, so, just like to maybe illustrate it a little bit. So maybe we have this graph with lots of vertices, and we want to know whether this graph is three-colorable. So three-colorable means that we can color it such that no two adjacent vertices would be in the same color. So a prover could come and say, well, this is blue, and that's purple, and that's green, blue, blue, and green. And then a verifier can just go over these the edges and say, well, this is not monochromatic, this is not monochromatic, this is monochromatic, and then in linear time we can deduce that. So that's an NP proof. Fine. Okay. And just like to give you maybe a reminder, so all right, still need to figure out how this works. Okay, just 1 second. Yeah, okay, sorry about that. So that's to say, you'll see here this avocado-looking shape. I will refer to it as the complexity avocado for now. It wasn't meant to be this way, but so these are the main protagonists, complexity protagonists that we'll have. We have P, which stands for polynomial time, as you know. We have NP, and we'll have P space. So, and it's kind of like important to keep this in mind, because now when we're talking about interactive proofs, we have this notion of proofs where, rather than as before, when we just had this graph and the prover colored it in real time, the prover gave us the entire coloring. Now we can have a conversation. And maybe we can go to the prover and tell him, I'm holding this particular edge. What are the colors of the vertices around? And, as we'll see later in this course, interactive proofs will be captured by the class of PSPACE. Okay. Now, lastly, the last model we'll consider today is that of PCPs. So what are PCPs? Okay, so this is a good place to focus, because it's an important definition. This is what we'll do for a while. And a PCP does the following thing. So we have a prover, just like in the NP setting, and the prover is sending a proof, exactly like in the NP setting. So what is different is that two things are now happening. The first thing is that the verifier, rather than reading the entire proof, like for example, an entire three-coloring of the graph, it will maybe just probe it extremely locally, maybe just like 3 different points. And of course, this comes with a price, as we had with polling and sampling. And the price is that we'll only we'll have to use some randomness in order to make this sampling. And also, we won't be able to know with absolute certainty. So for example, we can say maybe if we have a valid proof, then the valid proof will convince us. And if somebody is giving us a bad PCP, a bad proof, then after we will perform the sampling, then with very high probability, we'll manage to catch the error. And then you ask, what does it mean, high probability? And would we be happy with, probability of success of 90%? So, if I were to go on a spaceship and go to space, and I know that the system works with 90% probability, I wouldn't be happy at all. However, by simple ways of amplifications, we can easily boost these numbers to extremely small constants. Maybe we can do it to, 100 to the power of minus 50, which is, an upper bound for the total number of particles in the observable universe, and so on and so forth. So maybe we can get a chance of mistake which is so small that it's much more likely for the sun to explode, and we don't really have to worry about it. So that's what will happen in PCPs. Okay, so now I want to do this a bit more accurately and more formally. So let's see what's the definition of a PCP. So we start with a prover, which is an all-powerful prover, computationally unbounded, knows everything, just like in the NP setting. And we have some verifier, which is not only a polynomial time algorithm, but also an algorithm which is allowed to use randomness. We call this thing BPP algorithms. Okay, and now what is a PCP? We'll say that a PCP, and I will often maybe we will not make the distinction between the proof or the proof system. So when I say a PCP system, it would be a pair of a prover strategy and a verifier algorithm. And it would have these two parameters, like completeness, which would mean what is the probability of verifying the correct proof, and soundness, which would mean what is the probability of catching a mistake. So what will happen here is as follows. We want to say, let me kind of highlight it a bit. So if we have some X, which is a valid input, an input that we want to accept, then if we'll take the prover strategy, so think about the prover as just another algorithm which gets an input and produces a proof. For example, here is a nice prover for, an unbounded prover for graph recoloring. You run an exponential time algorithm, you somehow find the coloring, and then P of X would just produce this coloring. So it's just like a way of producing that. And then what we'll do is we'll say that the probability that the verifier will accept this proof is at least, 1 minus epsilon completeness. So, just to break it down a little bit, notice that first of all, that I have a verifier, and I will use the following notation. So when we use just the regular brackets, this is the inputs that the verifier actually see. So here we have X would be the input itself, for example, the graph that we want to recolor. And this row here would be some random string. Okay, and when we use something as an superscript, it just means that we'll have query access. So we'll make some random query. So it means that we can probe the object at particular points. So for example, we don't get all of the coloring, but rather we say, what is the color of, vertex number 7 or something along these lines. Okay, so that's the completeness. And okay, and let's maybe just proceed to soundness. And soundness would be pretty much what you expect. So soundness would tell us that if the input is not in the language, for example, this is a graph which is not recolorable, then regardless of any proof that we will give you, any malicious proof that claims that the graph is recolorable, we will still be able to reject. So we will say, like, we will not say this is a valid proof, except from some small probability of error. And I get here a question from Matthias, who asks if the verifier gets the randomness as input, then he should be polynomial time. Yes, so I agree. I mean, it really depends on your perspective. You can either say that this is a deterministic algorithm which gets random input, or just a deterministic, or just an algorithm that can flip coins. But for us, it would be just merely mostly semantics, but it's a good point. Okay, so these are the completeness and soundness conditions. And we kind of like say that the proof is a PCP if if it admits this type of approval strategy and the verifier. And that's exactly this notion of robust encoding that we will have. No, it's like it will allow us, instead of just reading the entire thing, we can only look at it locally. So the main point would be how many queries we'll make to this pi, for example. How many points we will look. Okay, and I will talk a lot about the proof size, you'll get to see it in a second. Okay.
I have a question.
Yes.
The prover. Basically, why do we have to introduce a prover to the definition in the first place? Why can't we just say that for every X in the language, there is a proof? And
that's a great question. We absolutely don't need to introduce the prover. The prover doesn't have to be an entity. So far, because it's like an all-powerful, it could be a completely existential statement regarding there exists a proof, and you don't have to be able to explicitly generate it. The reason why we want to adopt this perspective of a prover is that we'll later on try to see whether this can be done efficiently. So, for example, suppose that you want to delegate something to the cloud, and you want to generate some proof, then it wouldn't be nice if the prover, in fact, the PCP would have to solve 7 halting problems in order to generate that certificate. So that's like the entire question. But like excellent questions. Okay, so in the last lecture, when we talked about interactive proofs, the main heroes, the main protagonists in terms of parameters was what is the round complexity, what is the communication complexity, and so forth. In PCPs, we'll have 4 parameters that we'll care about. And so what I want to say is just like 2 things. I'll go over these parameters and explain what they mean, but then I'll try to zoom in on the things that we really care about the most. So the way I kind of like you to see it is, if you're seeing PCPs for the first time, then please just focus on the setting that I will tell you. And if you are familiar with this notion, then you can kind of like think about the rest of parameters and get into more details. So, okay. So we'll care about the proof alphabet, which means, when we make a query, for example, I get the color of a vertex. So how many colors can I see? And the reason is because if maybe I allow a really large number of colors, then maybe I can encode some crazy amount of information this way. We'll care about the proof length, which is, how long should the proof be? Can it be of exponential size? Can it be of polynomial size? And we'll see that there are trade-offs and a lot of interesting things regarding that. We will care about the verifier's query complexity. That would be a very important parameter, because the main thing we try to achieve with PCP is to verify a proof reading a small number of locations, maybe 3 ideally. And we'll also care about the amount of randomness, both as a resource and also because it's closely related to proof length. So now, just to zoom in, let's simplify things a little bit. So let's think here about completeness. Let's maybe think about epsilon c to be 0. And then this, this is just 1. So we want to always accept proofs with probability 1. And you see, in most cases, this is exactly what will happen. And here, where you see this epsilon s, maybe let's think about reject with probability half. And if you want to get a better number, then just repeat the whole thing several times. And in terms of the parameters, I want to encourage you to focus for now on the proof length and the query complexity. And the reason is because there is a close tension between these 2 things. The point is that, if we just start with an NP witness, then we can't expect to verify it locally. But the name of the game is how much redundancy we have to introduce, how much more structure and more information to allow this local to global phenomena. And so these two parameters will fight between each other quite a lot. Okay. So, and just like to give a better picture of what is happening, so we have the PCP verifier here. It's an algorithm, and we have the proof, which is just, some alphabet sigma, and we're of length L. We have the verifier making, Q queries, maybe 3 queries, and using some random string or some, coin flips that it made. And there we verify, and we need to say, to accept correct proofs and reject proofs which are far from correct. Any questions regarding the definition of PCPs or anything that I said so far? So in the meanwhile, while you're thinking, let me answer the questions in the chat. So there's a question regarding reducing the alphabet size, and we will see that we can reduce alphabet size, but there is caveat to that. Definitely, if it's like from one constant to the other, this can be done easily. But for example, if you have like alphabet size which is exponential, then things kind of get more complicated. And regarding quantifying what is the structure of a query, so I guess that I can be a bit more precise by what I mean. So think about, what is a query? So you have some vector pi, which is just like, some vector in L dimensions over like this set sigma. And a query means you provide an index and you get back the value. So, if this is like a string and that is x1, x2, x3, then you provide 1 and then you get back x1. Any other questions? And regarding the alphabet size, then it would everything that we will do here would be finite, because we're thinking about the settings of computer science, and we'll only deal with infinity in asymptotics, but we won't have any one can consider a PCP, for example, over the real numbers, but since it's being stored in a computer, then it would have to be some finite approximation of real number and things of this sort. And we'll see pretty soon in this lecture the difference between IP and PCP. Okay, so let me continue. Okay, so how do we build some intuition regarding PCP? I gave you this like rather cumbersome definition, and it's still kind of hard to imagine how it looks like. So let's try to take a page from Weierstrass' book and try to probe this object, see how it behaves in different settings. So, we want to understand PCPs with all of the parameters, but, as we said, we'll just focus for the moment at length and query complexity. So, let's start with some special cases and warm up a bit. So suppose that there is no proof at all. Let's look at how this model would look like. So no proof, how can we model it in terms of PCPs? We'll say, well, let's just fix the query to be 0. So if you can't query anything, then you can't look at a proof at all. So any thought is how would the PCP look like if we are not allowed to query the proof at all and we have no randomness? So what type of class this would be?
BPP?
So almost, it would be P because we have randomness 0, but exactly, like that is because we have, we said no randomness. Yeah. Okay, so indeed, there is P and no randomness. So now let me be a bit more, try to tackle you a bit. Suppose we still are not allowed to make any queries, so we can't see a proof, but now we are allowed to flip logarithmically many random coins. So, I can have an access to a log n bit string of random zeros and one. Yes, so as Matthias is saying, this is exactly still P. And the point is that because it's only logarithmically many random bits, and the whole thing is supposed to run in polynomial time. So, what we can do is we can just go over all possible random strings, 0, 0, 0, 0, 0, 1, and just like go one by one and see what would happen. And so we can roll if, that the vast majority, if all of them said yes, then we're happy, and if the vast majority, and then if a lot of them said no. So we can just like count. Okay. And now what happens if I get no queries and the randomness is polynomial? Exactly as Wilfred and Hilar said, as Wilfred said, we get BPP because we have no queries, so there's no proof. We can't access the proof at all. But we are allowed to use polynomial many like random coin flips. So this is exactly just a polynomial time algorithm which is allowed to flip some coins. Good. And now suppose that we are playing the other game. There is no randomness at all, like completely deterministic verifier. So what would happen if we are allowed to make polynomially many queries to a proof? Exactly. So as Ida is saying, we're getting NP because in some sense, it's like we get some proof and we're reading the entire thing. So we just get an NP proof. Nothing is happening. Okay, so what we'll do is when we'll say PCP without all of these parameters, we'll get something really nice. It would try to capture the notion of polynomial time algorithm. So what does it mean to capture polynomial time? It would mean that the number of queries that we're allowed to make is polynomial. The randomness is polynomial, as you would allow an algorithm. It runs in polynomial time, so you can flip poly n coins. And it would allow for proof of size exponential and alphabet, which is of size exponential. And does anyone see why we can allow proof of length, which is exponential?
Because to express an index in that proof, you're going to need a polynomial number of random bits.
Exactly. So the point is that, we can kind of like somebody can write down on a piece of paper, a very long piece of paper, or maybe somewhere on the internet, this incredibly long exponential size proof. And what we'll do is, we just want to query it. So all we have to do is specify the index I, and that takes log the length of the proof, which would allow us to do things. And the same with respect to the size of the alphabet. Okay. So now, we have this model, and we kind of like try to see the extreme cases, and we see, well, somehow like where the notion is not interesting, but now we want to see where it is interesting. So we need to kind of ask, one of the most natural questions is what languages have PCPs? Like, where in this whole complexity hierarchy we can have PCPs? So we know we can do BPP. We know we can have emulate randomized algorithms, and we know we can do NP. But how far can we go? And we can ask, even if we don't want to go beyond NP, even if all what we care about is verifying tier for NP, so can we do something which is more efficient with a PCP as opposed to an NP witness? Can we verify it quicker? Can we use just like small number of queries? What can be done? Another question is like whether we can use PCPs for tractable languages, for languages that we actually don't really need. Like we don't have to have approval, but it could help us. Can we verify just faster than execute? This is like what we care about a lot in delegation settings. And we'll also care about, can we have zero knowledge PCPs, which would preserve privacy and things along these lines. Okay, so let's go and then see what the answers are. So regarding what languages have PCPs, so we see that it's more than PSPACE. So if we're competing with the interactive proofs course, then we're winning. Interactive proofs are contained in PSPACE, and we will go beyond that, and we'll see exactly well. So it's an extremely strong model. And yes, we have amazing benefits for NP languages. We can verify statements in polylogarithmic time. And it's also allow for these doubly efficient ways of verifying things, which is effective, in which all parties are super efficient, and also regarding zero knowledge, all of these things can happen in PCPs, right? So that's like lots of good news. And we should be, kind of happy with that. It's not, it's pretty much all the things that we can hope for. But one also has to be careful when we talk about PCPs, because the model is non-standard. It is a bit confusing. For example, if we can have like a proof of exponential size, then how do we get this exponential size? Where is it written? I mean, can this actually be useful for anything? Right? It's a bit confusing. And I want to give like two answers out of many. So one of them is that even if the proof length is, so first of all, we'll see that there is a lot of work where we can make the proof extremely short. In fact, just a little bit more than linear. And also we can compile these type of proofs into, using cryptography. So we can use these PCPs as a backbone for a lot of positive results regarding proof systems. And also it led to an entire beautiful area, which the positive results of PCPs can help us show lower bounds and show hardest approximation. And we will touch all of these things later. Yeah. Okay, so I see that, and questions during the chat were answered. And feel free at any point, to unmute yourself if there are more questions. Okay, so let's start with, getting some intuition regarding PCPs. And I want to give you some simple upper bounds on PCPs, like how far can they go? And potentially you can say, maybe a PCP can, solve halting problems. Maybe it can do, insane things. And what we'll show, and again, the complexity avocado is starring here, is we'll show that PCP is at most NX. So that to remind you what is NX, it's kind of NP, where instead of having things in polynomial, you have things in exponential. So you have exponential time and exponential size group. So if you think about it, pretty much any imaginable problem which was not, annoyingly designed to be outside of NX would be in NX. I mean, of course, you can be clever about it and find problems outside of it, but anything that we might possibly care about should fall naturally within NX. And we'll see that PCPs cannot do more than that. So how do we do that? So we'll do it by proving two tiny lemmas. Each of them would be just a line of a proof. And it goes as follows. So, it might look first scary just because of the notation. So let me just say what's happening here. So we have L denoting the proof length. And we have R being the randomness of the variable. So now I want you to just look at the first bullet, because that's what we care about. So I want to give you an argument would say that the proof length is kind of being controlled by the randomness of the verifier. So what does it mean, first of all, non-adaptive? So just like to quickly say, so you have this proof string, like this proof string, and a non-adaptive verifier would throw some random coins and choose locations to query. An adaptive verifier might, read the first coordinate, see, aha, I see 7, and based off that decide to make a different query. But for our case, let's focus first on the non-adaptive case, which is the one which we see the most anyway. So this lemma will essentially tell us that randomness bounds the length of the proof. And why is that? So the idea is that, well, suppose that I'm giving you, an infinite size type of proof, but you're only allowed to use R random strings, and you're making Q queries. So for each random string that you have, you choose your Q queries, right? So you have total number of 2 to the R possible random strings of length R. And for each of one of them, you'll make Q queries. And so this bounds the amount of length. So it doesn't make any sense to give a longer proof because we'll never query it anyways, because just like everything, we choose some randomness, and for each R we have a set of locations. So yeah, so that's bounded. And even if the verifier is allowed to be adaptive, then this doesn't change much. So we get the exact same expression, 2 to the R and Q. But now, maybe we made the first query and we saw some number between 1 to the size of sigma. So, maybe we saw 7, and so we change our strategy. But we just like multiply it by the number of answers that we see to each one of our queries. And still, this is a total number of queries that we will make. So in some sense, all this lemma is telling us is because the randomness that we have, and maybe the outcomes, determines which places we will probe the object, then it makes no sense to have a longer proof. Or, without loss of generality, if it's never being asked by the verifier, then just drop it. So that's all it says. And the second lemma is kind of like a de-randomization lemma. So what do I mean by de-randomization lemma here? It kind of like tells us, well, I want to place, so let me just like give the definition first. I want to place the class PCP with a proof of length R, and where we are allowed to throw R random coins. And I want to say, can I do it in, maybe not NP, but N of time something. So that when I'm saying N time, I'm just, it's saying, it's like NP, only instead of polynomial, I have, time being parameters. So for example, if I write N time of poly N, that's exactly NP, and N time of X, then that's exactly NXP. So, okay, so going back to that, essentially what this lemma will tell us is that if I want to take a PCP and I want to emulate it by an NP proof, in a sense, maybe, an NP proof of a longer size or a longer propagation, I can always do it in some way which is bounded by the randomness. Now, the first part of it, like emulate, suppose that I didn't have randomness at all, then this would have been trivial, right? Because like you have a PCP of length L, so you can verify it in NP time L just because, you take the PCP oracle and you read the entire thing. But because we have randomness, we kind of need to be able to de-randomize it. So it would be similar to what we saw before. Let's dive into it, and I think it would be quite clear. So, we start with our PCP system, some prover and a verifier for a language L, and we know that we're using these R random bits to query a proof. Okay, all nice and well. So now we'll define this decider function, which might look scary, but it's actually an extremely simple one. It just tells us that for any random string, we will compute what the verifier would say if we chose this random string. And then we will say 1 if and only if we are passing the completeness threshold. So if you recall before, when we had exactly the same argument. So what do we want to do? We want to start with the PCP verifier. If the PCP verifier is guaranteed maybe to always be right if this is a yes input, and to always say 0 if it's not to always to say 0 with probability 1 over a half. So we have like the completeness threshold here. It could be 1 or it could be like 2/3 or whatever. So what we're doing is we're saying, let's run the thing over all possible random strings and just count with respect to the randomness what is the fraction of the algorithms which said yes. So if I go, for example, let's suppose that the error of completeness is 2/3. So I run the algorithm over all possible random strings, and if I see that at least 2/3 of them accepted, then I know that the algorithm that the PCP would have accepted. So this is a way for us to emulate the PCP simply by just removing them randomness by enumerating over all possible random strings and doing so. And that incurs exactly this exponential cost in the size, in the length of the proof, in the total number of randoms. Okay, any questions regarding this argument? So it's all very simple arguments, but if you see it for the first time, it can be confusing. So I just encourage you, if anything is not clear, you can either ask now or on Slack, and we'd be happy to help with that. Okay.
Just on the first lemma, is that like without loss of generality, L is less than or equal to, and L is less than or equal to, or is it like a requirement on L?
Yes, it is, exactly. So what it essentially tells us is that there is no, I mean, syntactically you can have a longer proof, but it will buy you nothing. And so we will always assume without generality that we have that. Yes.
Okay, thank you.
Okay.
Just one question. So the proof that you wrote in the previous page, where are we using the non-deterministic time? Couldn't we just say deterministic time?
No. Okay. So crucially, the non-deterministic time, it means that we have a proof. So think about, in order to emulate a PCP, you need someone to produce this, this three-coloring of graph. Yeah.
That's right.
Okay. Good. So, we got some upper bound on on PCPs. So we know that they can't do more than an X. So, the complexity avocado suffices for describing everything that we want to do with respect to PCPs. That's our entire universe. And one thing that we can easily do is get PSPACE. And well, just a reminder, PSPACE, it's all problems that can be solved using polynomial amount of space, which also captures like NP and co-NP and all of these things. Okay, so why does that hold? So it's a very, very, very simple argument. And maybe before actually proving it to you formally, let me just sketch the idea. So we have two things going on. The first one is we'll show that interactive proofs can be emulated by PCPs. And then because, as we will show later, PCPs interactive proofs are equal to PSPACE, then we get the entire thing. Okay, so now the name of the game is to say, suppose somebody is giving me some interactive proof. How am I supposed to emulate it via a PCP? Anyone has an idea? So just to inspire you while you're thinking, let's see what is an interactive proof, another way of looking at an interactive proof. So you can kind of think about a tree. And well, maybe here you have a layer which corresponds to the verifier. And the verifier sends a certain message to the prover. Now, based on that, the prover needs to respond with some answer. And then again, the verifier sends its own message, and like this correspondence of verifier message, proof message, exactly would correspond into all, to a path down that tree. And exactly as Matthias is writing down in the chat, and also Philip, the point is that what we can do is the prover can commit to the entire strategy. So the proof could be like saying, this is what I would say with respect to anything that you might ask me. So, and the moment that we have that, we can just emulate it, right? Because the prover is writing down the strategy that it will be using. And so it has nothing else to give us. So just to do it a bit more formally, so what do we have? We start with some, interactive proof, and let's assume that it is public coin. As you'll see later, we can do it without loss of generality. And this means that the verifier is not sending any sophisticated messages. It can just send random bits. So it's just a type of an interactive proof where, prover sends something smart, and then the verifier just types a large random number. And then the prover says another something which is smart, and then you respond with randomness. Okay, so we can do this kind of thing. And then we can look at how the transcript would look like. So again, this is a scary looking expression, which means exactly what we said before with the tree. So, for a random, for a verifier message R, some randomness, the prover would respond with A of R. And then this is like emulating the first round. And then in the second round, well, the verifier sent both R1 and R2. And the prover needs to give an answer for each one of these R1 and R2, and so on and so forth. At the end of the protocol, we send k different random strings, and the prover responds with respect to each one of these things. So, the only thing which is happening here is that the answer of the prover might not only depend on the random string that it gets at any particular round, but also on the entire history of the conversation. That's all. So, and then we'll take just the PCP verifier, and then we emulate the run of the IP just by, choosing what we want to say and interacting with the IP, with the interactive prover in our head, which we can now, because we know what it would have said in each case. And, completeness would hold trivially. So if we have X, which is in the language, so there is an honest proof, and now we have, an honest conversation with the prover. For example, the prover could maybe say, if I ask regarding the color of vertex I, it's blue. And so we just can emulate the conversation and everything will go according to plan. And if the prover tries to cheat, so the point is that because the prover kind of reveals the entire tree, like the entire tree of interaction, then if it has any malicious strategy, it would have to correspond to some branch of the tree, and so the entire thing can be emulated exactly. Okay, so that's that. And just to conclude, it means that, well, PCPs, they lie somewhere between PSPACE and an exp. And we'll try to pin it down, and we'll actually prove exactly where PCPs lie. And we'll actually show that it's the more optimistic scenario, and any language in NX admits a PCP. And we will actually see a full proof of this theorem, which is, at least if you ask me, one of the greatest gems of theoretical computer science. It is a beautiful, beautiful proof and so many beautiful ideas. So I hope you'll enjoy it as much as I do. And we'll do it by using some techniques that we'll see from interactive proofs, and also some, sparkling brand new one with some really nice mathematical structure. Okay, and we'll also see how one can take these PCPs for an exp. And recall that these PCPs might have, exponential lengths proofs and all of that thing. And we'll see that we can kind of like gracefully scale them down so that we will have a PCP for NP, but with polynomial size proof and logarithmic runtime. Okay, so let me continue. Okay, so maybe before I see another question. Before we proceed with that, so let's see. So Matthias is asking regarding the size of the tree. So if you go back, I think this would help to the slide. Let's see. So regarding the amount of information that we have to store, then notice that we have the first random string, and for that we have to store the answer for the first question. And then we look at R1 and R2, and we have to store all possible answers. And then if you just count the total number of messages that has to be asked, then you see that it's all being done in like this exponential in the size. Okay, so let me just go next. So I want to tell you in the time that I have left, just a bit about what's going to happen in the course. So we had this soft introduction, and things are going to get really interesting starting tomorrow. So I want to tell you about the different components and how they relate to each other, and also to give you some escape points. And by that I mean the course is designed in 3 sub-chunks. So even if at some point you feel a bit lost, then 2 lectures down the road we start something new, which you can just build on the previous thing in a black box way, so you're never quite lost. Because it is quite challenging. Typically when we give such a course, it's being done over an entire semester. And then if you miss something, you have a lot of time to fill it in between one lecture and the other. Here it's quite a bit of intense. We meet every day, and so it's good to have that. And just like to see another question by Surya, just saying, just to clarify, the only restriction on the resources for PCP is the verifier time runs in polynomial time. And yes and no. I mean, yes, when we just write PCP without any quantifiers, then we mean yes, the restriction is exactly that. But often we will also zoom in on the parameters, and we'll insist that we only make 3 queries, and maybe the proof is of size which is polynomial or maybe quasi-linear, and so forth. And you see that I missed a question. Oh, Aviv asked regarding zero knowledge, and yes, and whether the proof will be different. So we'll see that when we're talking about zero knowledge PCPs, then actually even the mere definition of a zero knowledge PCP is a whole lot trickier than what one might imagine. Because like zero knowledge proofs somehow require creativity in the definition, and that's for interactive proofs. And when you consider PCPs, things get a whole lot more complicated. And we'll see that in detail next week, exactly how zero knowledge PCPs are defined and how it would work. Okay, so let me quickly continue with the course outline. So we'll start by purely mathematical expedition over the first 3 or 4 days, where we'll kind of like consider this notion of local to global phenomena. And this would be the mathematical framework upon which we'll build in order to get all of the magic of PCPs. So what we'll cover is something which is called linearity testing, low degree testing, and we'll see some, fast Fourier transform based way of testing univariate polynomials. So what do I mean by all of that? So I have a next slide that will kind of explain exactly what I mean, but in some sense, this would be, we'll define this way of enriching data such that it would admit this nice local to global phenomenon. But then we'll have to verify and check that, this structure really exists. And this is something which really, brings the best and nicest math in theoretical computer science, in my opinion. And I hope you'll enjoy it as much as I do. And then we'll have quite a bit of PCPs constructions, and we'll see them in various type of settings. We'll see how to use exponential size proof, something which is extremely long, but only off one local. So if you need to make 3 queries, and using these 3 queries, you can verify an extremely long proof. And then we'll see another PCP which kind of complements that. Well, the proof is polynomial sized and well behaved. But you need to make like polylog queries, so the locality is not amazing. And we later see a notion of PCP composition, which means how we can get the best of both worlds. So it's like we see a composition theorem which tells us, you can take this this great locality but poor length, and this great length and poor locality, and just get the better of both worlds simultaneously. And we'll also see that all of these things kind of like scale down nicely, and we can in fact do and verify any problem in NP in logarithmic time, as opposed to so linear time or polynomial time. And finally, we'll discuss some applications. And it's really a question of whether you glass half full or glass half empty type of person. So on the one hand, we'll see delegation of computation. That's for the positive people among us, where we kind of like will use PCPs in order to actually verify computation, in order to, for example, delegate information to the cloud, to allow for this like zero knowledge snarks and all of these beautiful things you see now being deployed on blockchains and being applied in practice. And for the pessimistics of us, we'll see how to prove lower bounds, and show how computational tasks are extremely hard, which is in some sense, perhaps the main goal of complexity theory, which is something at least that I care about a lot. And just to conclude, I want to give one last slide and talk about a bit of perspective, technical or conceptual perspective. So there are two themes that we're going to see in this course, which will happen with a recurring theme. And we've made a choice of not being too explicit about them because we don't want to have prerequisites, but I will keep hinting to these things throughout the time. And so those of you who are familiar with them will find themselves easily. So the first one is this notion of property testing. And what is property testing? So in a nutshell, it just tells us, suppose that we want to get these algorithms which are extremely fast. So you don't want to, you have some problem and you want to solve it. Let's go back to the, I don't know, free coloring problem or anything of this sort. And you're saying, well, the input is so large that I can't hope to read the entire thing. For example, it could be an exponential size proof that we want to verify. So how can I solve a problem without reading the entire input? So the answer is you can't. I mean, what happens if like the input is bad at the one place that you don't read? Then you'll make a mistake. However, if you're allowing a relaxation where you say, well, let's say that pi is maybe the set of all three colorable graphs. And let's look at the neighborhood, the epsilon neighborhood of graphs. So here we'll have graphs which are not three colorables, but by just tweaking a few edges, you can make them three colorable. And outside in the red area, you'd have things which are quite far from being three colorable. So a property testing algorithm is an algorithm which only probes a tiny, minuscule fraction of the input and still able to distinguish whether you are exactly in the property or whether you're far from having the property. So this is, on the one hand, something that would be quite a driving force for us. And, maybe if we go back to the example of polynomials, so maybe you're getting this function f, and you want to know, is this function a polynomial of degree at most d? So obviously, and you're getting just the truth table of its evaluation. Obviously, if you don't read the entire thing, you can't know. But if all you want to know is whether it's exactly a low degree polynomial or something which is very far from a low degree polynomial, then as we'll see, we can do it extremely efficient. And now you might say, how is that related to PCPs and what we're trying to do? So the idea is that we'll also have this complement part of coding theory. And the kind of like coding theory in a nutshell, it tells you, let's take some domain. Well, maybe we have this X and we have this Y, and they might be like really close to each other. And let's artificially create distance between them. So what do I mean by that? We will map them into some other domain, maybe, so maybe it's function C. And the point is that every pair of points, even if they started like only different by a single location, they will be mapped into these images, these like code words, which we'll call them, which are extremely far from each other. You might ask, why would I want to have that? So, and the answer, at least in the setting of PCPs, is that this is exactly where the property testing algorithm would be complementary to that. Because we'll take an object, we'll use a code in order to create this rich structure that in particular will create this distance, and then we can just run the property testing algorithm. So if you go back to the voting example, so the coding theory part would be about taking a piece of bread with a bit of jam on it and smearing the jam uniformly, and the property testing part would be about how to take a random bite and get a taste of that jam. So that's like and these two parts will complement each other and we'll kind of explore both of them. So for example, just like to briefly go back to the previous slide. So when we said, linearity testing, so linearity testing would be to check whether a function is linear, and that would correspond to a code which is called like the Hadamard code. So in fact, we'll see what is the Hadamard code and how to have a property testing algorithm for it. And with low-degree polynomials, we'll have the Reed-Muller code, and with univariate polynomials, we'll have the Reed-Solomon code. And so it would all kind of like play together into something nice. Yeah. And just to give some examples of this type of objects of code, which we'll actually explore massively, is exactly polynomials of low degree and linear functions on the hypercube and things of this sort. Okay, so this is all I wanted to say. I'll now stop the recording, but I will still stay if you want to ask me some more questions. And let me just stop.